have seen what photochemical reactions are, what is the difference between photochemical reaction and thermal reaction, and also the various laws of photophysical, or we can say photophysical laws. Now, another aspect in photochemistry is the Jabalonski diagram. Now, in this video, I shall be explaining to you, or I shall be introducing to you the term Jabalonski diagram, and how do we depict Jabalonski diagram, how do we draw Jabalonski diagram. Now, Jabalonski diagram is a representation of electronic excitation. Now, what are all these? We shall see. Now, we have photochemical reaction, which depends upon, or which is concerned with the chemical effects induced by light radiation, particularly the UV visible light, which falls in the range of wavelength range of 200 to 800 nanometer. So, both light absorption happens and light emission happens. We will be studying both these phenomenon when we discuss about photochemistry, both emission and absorption of light. Now, when light is absorbed or light is emitted, photochemical process happen and photophysical process happen. Either of these two can happen, either photochemical process or physical process can happen. Now, what is photochemical process and photophysical process? Now, when molecule absorbs light or is irradiated with light, and then it absorbs light, and if it is getting converted to a product, an entirely different chemical, then we call it as photochemical process. There is a chemical change happening because of the light radiation. Now, photosynthesis is an example of photochemical process. Ozone depletion is an example of photochemical process. In photosynthesis, water and carbon dioxide is getting converted to carbohydrate in the presence of light. So, light is absorbed and water and carbon dioxide is converted to carbohydrate. While in photophysical process, what happens is the molecule absorbs light, it goes into excited state, and then it comes down to its normal ground state with the emission of the energy. So, when light is radiated onto the matter, onto the compound, it absorbs light, it gets excited, it goes to higher energy state. From the higher energy state, it comes back to the ground state with the emission of energy in the form of light. Okay, so, there is no chemical change happening, there is a physical change happening, and you get back the reactant, or you get back the original molecule. So, that is photophysical process. Phosphorescence, fluorescence, etc. falls under this category, photophysical process. We will be looking into detail about what is fluorescence, what is phosphorescence, etc. Now, we will take photochemical reaction. We have this reaction wherein molecule A absorbs light, goes to excited state, and from that excited state it gets converted to the product P. Now, we can split this reaction into two. The first step is the absorption of light and getting excited. Now, that is the primary process. Okay. So, for the primary process, presence of light is essential. So, in the primary process, the compound absorbs energy, absorbs light energy, and goes to excited state. Now, the next step is this excited state, or this excited molecule gets converted to a new compound product. Okay. Now, that can be considered as the secondary process in photochemical reaction. So, photochemical reaction is a two-step process. You have the primary process and the secondary process, and for primary process light is essential. The secondary process can happen in the presence of light or in the absence of light. Light is not essential. You have got light reaction and dark reaction in photosynthesis. That is an example of this primary step and a primary process and secondary process. Now, when you consider photophysical process, what is happening? Light is absorbed by the molecule, it goes to excited state, that is a primary process. So, in both the cases, in both photochemical process and photophysical process, the primary process is the same, or the primary step is the same, that is the light, the molecule absorbs light and goes to excited state. But in photophysical process, what happens? From the excited state, the molecule comes down to the ground state with emission of energy. The emission of energy is in the form of light radiation, or falls in the wavelength 200 to 800 nanometer. So, there is no chemical change happening, but in photochemical reaction there is a chemical change happening. You are getting a product P, you are getting an entirely different compound, but here you are getting the same compound. You start with A, you end up with A with some amount of energy, and that energy has been absorbed or obtained from this radiation, from the light. All right. So, these two processes literally involves electron excitation. So, we know that every chemical reaction involves electron transfer or sharing of electrons. In fact, it is the electrons which are responsible for chemical reaction, and in photochemical reaction it is the electron excitation which is responsible for the reaction to happen. So, both for photochemical reaction and for photophysical process, it is the electron excitation that is happening. All right. Now, if we study this electronic excitation, we need to know how do this electron excites and what happens after excitation. Now, for that we need to know a bit of the quantum mechanical aspect of the molecule of the electrons, and we know that every molecule or in every system, the electrons remain in the paired form. If wherever possible, they remain in the paired form, and when they are in the paired state, the electrons will be in opposite spin. One will be having plus half and the other one will be having the value minus half. Now, that is the spin quantum number. Now, we use the spin quantum number ms to explain the orientation of electron around its own axis. Now, spin quantum number has got two values, plus half and minus half. If the orientation is in the clockwise direction, we say that the value for spin quantum number is plus half. If it is in the anti-clockwise direction, we say that the spin quantum number value is minus half. Now, here I have shown depicted two electrons which are in opposite spins. Okay. So, one electron will be having the value minus half, the other one will be having the value plus half, and the total spin will be equal to 0. Now, the total spin S, it is the total sum of the total spin angular momentum, or sum of all electron spins. Now, in this case S is equal to 0 because you add plus half and minus half, you get the value 0. So, that is S is equal to 0. Now, from the total spin you will get what is called spin multiplicity. Now, spin multiplicity helps us to get an idea about the stability and energy of the electronic states. Now, spin multiplicity is calculated using the equation 2s plus 1, where s is this total spin momentum or angular momentum. Now, in this case, when the electrons are paired and if the electrons are in opposite spin, then S will be 0 and the spin multiplicity will be equal to 1, and we call that the state is in the singlet state. When the spin multiplicity is 1, we say that the electronic state is in the singlet state. So, that is one possibility when there are two electrons. Now, the other possibility is that these two electrons are having the same spin. When they are having the same spin, that is either the spin value will be either plus half or it will be minus half. So, both these electrons will be having spin quantum number plus half or minus half. If that is the case, then S value will be equal to 1. When they are paired with opposite spin, the S value will be equal to 0, but here it will be 1. You add two halves together, you get 1. and their spin multiplicity will be equal to 3. 2s plus 1, 2 into 1 plus 1, that is 3. And we say that that state is triplet state. Okay, that is when spin multiplicity is 3, we say that it is a triplet state. Now, every system tries to increase the spin multiplicity. Now, the reason is when the molecule, when the electrons are in opposite spin, there is possibility for exchange energy. The exchange energy is possible. The exchange of electrons are possible within the same energy level. Because of that, the energy of the system will be lowered, and hence the molecule or every system tries to attain triplet state or to increase the spin multiplicity. And that is the basis for Hund's rule of maximum multiplicity, wherein we say that pairing of electrons happen when all the degenerate orbitals are singly occupied. So, if there are 4 electrons, the first three electrons will occupy the degenerate orbitals, and then the 4th electron will go for pairing. It is not depicted like this. So, in the first case the multiplicity is more, but in the second case the multiplicity is less. So, in the first case we will be having lower energy than the second case. So, this is acceptable, this is not. All right. So, triplet state has lower energy than the singlet state, and hence triplet state is more stable. So, this concept you have to keep in mind when we are moving on to Jabalonski diagram. The triplet state has a lower energy than the singlet state. Now, let us see how we can depict this when energy levels. Now, say suppose we have the 2 electrons in the ground state, singlet ground state, which is depicted as S0. The 2 electrons are in the same orbitals. Okay, they are having opposite spin. So, they are in the singlet state, they are in the lowest energy level, that is depicted as S0. Now, when a molecule is irradiated, the electrons get excited and it goes to higher energy level. One of the electron jumps to the higher energy level. Now, when it jumps to the higher energy level, the spin multiplicity is retained, or you can say there is conservation of spin multiplicity, or you can say that the spin quantum number is retained. So, it is in the same quantum number as it was earlier. So, these 2 electrons are even now having opposite spin. So, this electron which has been moved on to the higher energy level has reached the S1 state or higher singlet state. Now, here again the multiplicity is 1, because S is equal to 0, as you see here both of them are having opposite spin. Now, this is depicted as S1, the energy state or the electronic state is depicted as S1. Now, there is another possibility. When the electron gets excited, what happens? It moves on to higher energy level with the spinning of its spin, the spin is changed. All right. So, some amount of energy is used up to change its spin. Now, you can see here the electron spin in the ground state and that of the excited state are same. So, there has been a reversal of spin. Now, when you see here the reversal of spin has happened and hence the spin multiplicity is 3, you can say that this is the triplet state. Now, we usually show that the triplet state energy level is lower than the singlet state energy level. Now, some amount of energy has been used up to change the spin of the electron. It has gone to and hence the energy of the triplet state will be at a lower level than the singlet state. So, first excited singlet state will be at a higher energy level than the first excited triplet state. So, these are the 2 possibilities of electron excitation. So, this will be S0 and the other one will be T1, that is first triplet excited state. Now, we can depict this energy level in the form of an energy profile diagram. On the x axis we can take the energy Now, here you have the ground state, singlet ground state, which is shown as S0, and then we have the first singlet excited state, which is shown as S1. Now, as I had said earlier, the 2 electrons are here in the ground state. These 2 electrons are of opposite spin. They are irradiated. One of the electron moves on to higher energy level, to the higher excited state without any change in the spin. It will remain in the singlet state itself. Okay. So, you can say that the electron moves from ground state to first excited state. Now, the electron is at a higher energy level, and we know that no system prefers to remain in the higher energy level. It will always try to come back to the ground state or to the lower energy level. Now, that is possible, and this is called relaxation. So, when the electron goes down to the ground state from the excited state, is called relaxation process. When the electron goes from ground state to higher level, we call it as excitation process. So, after excitation we have relaxation. Now, this relaxation can be of 2 types: radiative relaxation and non-radiative relaxation. When the electron goes down to the ground state with the emission of light, then we say it is radiative relaxation, or with the emission of radiation, we say it is radiative relaxation. But if there is no emission of radiation, but there is exchange of energy, then we say that it is non-radiative relaxation. That is, the molecule or the electron goes down to lower energy level with the exchange of energy from the excited molecule to an unexcited molecule. We say it is non-radiative relaxation. There is no emission of radiation happening there. So, there are 2 types of relaxation: radiative relaxation and non-radiative relaxation. So, when the molecule or the electron from higher excited state goes down to lower to the ground state, electronic state, if it goes down in this way with the emission of radiation, it is a radiative relaxation, and here it is moving from first excited state to lower ground state, we call it as fluorescence. When the electron goes from higher energy level to the lower energy level, from one higher electronic state to lower electronic state with emission of radiation, we call it as fluorescence. So, the fluorescence is a radiative relaxation. Now, once the electron has gone to S1 state, it can undergo relaxation with a change in its spin. So, here from S0 to S1, the spin has not changed, but then from S1 it can change its spin and go to triplet state. Now, that is called intersystem crossing. So, from singlet state to triplet state, transfer of electron from singlet state to triplet state with the loss of some energy. The energy is used up for the change in spin. So, the spin has been changed and it has become parallel to the spin of the electron on the ground state. Now, here there is no emission of radiation. So, intersystem crossing or ISC is a non-radiative relaxation. All right. Now, from this triplet state, excited triplet state, the electron can go down to the ground state, singlet ground state, okay, with the emission of radiation. If that happens, that is from triplet state, higher excited triplet state to ground state, singlet ground state, then it is called phosphorescence, which is a radiative relaxation. Now, there are other non-radiative relaxations. Now, here you can see the various energy state has been depicted, electronic state has been depicted as S0, S1, S2, S3, etc. And within each electronic state there are vibrational energy levels V1, V2, V3, etc. Now, within each vibrational energy level there are rotational energy levels also, which has not been depicted here in this picture. That is beyond our scope. Now, we need to consider only the electronic states and the vibrational energy level within the electronic states. Now, when we excite a molecule with radiation, what happens? The electrons can move from the ground state S0 to the first excited state, and there itself it can go to the lowest vibrational level of the first excited state, or to the first vibrational level of the first excited state, or to the second vibrational level of the first excited state, and so on. Or if it absorbs more energy, the electron can move from S0 to S2 or to S3, and there also within there also you can have different to the different vibrational levels. Now, when the electron absorbs light and goes to higher energy level, if it is in the higher vibrational level of the excited state, it can come down to the lower vibrational level of that excited state. Now, here you can see the electron has jumped from S0 to the 1 to 3rd vibrational level of the first excited electronic state. From there, it is coming down to the lowest vibrational level of the first excited state of the same electronic state. Now, that again does not happen with the emission of radiation. Okay? Now, that is called vibrational relaxation. That is another non-radiative relaxation mode. Okay? Like our intersystem crossing, you have got vibrational relaxation. Now, it is based on this that we have the Jabalonski diagram. Now, Jabalonski diagram represents the energy transformations that can result from the absorption of UV visible radiation by a molecule. We will be depicting the energy transformations, we will be depicting the electronic transitions when a molecule absorbs light radiation. Now, that depiction is called the Jabalonski diagram. Now, it is quite interesting when we pictorially represent the energy excitation of the electrons. Now, here we have the various electronic states as I had mentioned earlier. All right. So, you have the lowest electronic state S0, singlet excited state. You have the next higher singlet excited state, that is S1, then next higher S2, then next higher S3, and it can go on. And when you look at this, you can find that as you move on to higher electronic state, the energy gap between the electronic states are less. The energy gap between the ground state and the first excited state is more than the energy gap between the first excited state and the electronic state and the second excited electronic state. And within each electronic state, you have got the vibrational levels. So, the bold horizontal lines over here represents the limits of electronic energy states, and within each electronic energy state we have multiple vibrational energy state, which are shown with thinner lines and depicted as V1, V2, V3, etc. Now, as the electronic energy state increases, as I said earlier, the energy difference between the two electronic states decreases, and as it moves higher, we find that all the electronic states overlap. It appears to be a continuum. Now, when we discuss about the photochemical processes, we are more concerned about the transitions happening between the S0 level, S1 level, S2 level, not more than that, and also from S1 to T1 between singlet state and triplet state. So, Jabalonski diagram will be involving only so much of energy levels. Okay, the singlet states and the triplet state, and that also singlet first excited state to the maximum of second excited state. Now, let us have a look at the Jabalonski diagram. We are going to in detail into how the Jabalonski diagram appears and what are the informations that we will get from Jabalonski diagram. Now, when the electron moves from lowest vibrational level of the ground state to the lowest vibrational level of the singlet excited state. It can move there. It can go to the next higher vibrational level of the first excited state, and it can move to the next one. So, it can, depending upon the energy of the light absorbed, the electron or the molecule can move on to the various higher vibrational levels or higher electronic state. So, the fifth line which I have shown goes from the S0 level to S2, that is the second excited state. The fourth line goes from S0 to the third vibrational level of the first excited electronic state. Now, from there, from the different higher vibrational levels of the first excited electronic state, the same multiplicity, it is in the same singlet state, it can come down to the lowest vibrational level of the same excited state. Now, that is vibrational relaxation, as I said earlier, and that is a non-radiative transition or non-radiative relaxation. Now, another possibility is that from the lowest vibrational level of the first excited electronic state, it can move down to the ground state with the emission of light or with the emission of radiation. When that happens, we call it as fluorescence. So, it can happen from the higher vibrational level of the first electronic state to the various other vibrational level of the ground state. With the emission of radiation, we call it as fluorescence. All right. So, F is depicted as fluorescence, which is a radiative transition or radiative relaxation. Now, another possibility is that from the higher vibrational energy level of the first excited state, it is coming down, it is undergoing vibrational relaxation. The electron goes to the lowest vibrational level of the first excited state, and from there it switches on its spin, the electron spin changes, and then it goes to the triplet state. Now, that is called intersystem crossing, ISC, which again is a non-radiative relaxation. Now, from the higher vibrational level of the triplet state, it can go down to the lowest vibrational level of the triplet state via vibrational relaxation. Again, vibrational relaxation can happen, non-radiative relaxation. From the lowest vibrational level of the triplet state, the electron or the molecule can come down to the ground state. Okay. It can come down to the various vibrational levels of the ground state. Okay. If it happens with the emission of radiation, then we say that it is phosphorescence. So, the difference between fluorescence and phosphorescence is, in fluorescence, the electron movement is from between two different electronic states of the same multiplicity, but phosphorescence involves an electron transition between two different electronic states of different multiplicity. Fluorescence involves from S1 to S0, but phosphorescence involves movement of electron from T1 to S0. We will be discussing it in detail later. All right. So, P stands for phosphorescence. Now, when after phosphorescence, if the molecule is in the higher vibrational level of the ground state, it can come down to the lowest vibrational level of the ground state by vibrational relaxation. Now, another possibility is, from the ground state, the electron is transferred or the electron gains energy and goes to the higher vibrational level of second electronic state. All right. From there, it comes down to the higher vibrational level of the first electronic state. So, here it is from V1 of S2, it is going down to V2 or V3 of S1. Now, that is called internal conversion. Okay. Internal conversion happens between the same electronic state, same multiplicity electronic state of different energy levels between S3 and S2 and S1. Internal conversion will not happen between S1 and S0. That is because the energy gap between S2 and S1 is less when compared to the energy gap between S1 and S0. So, internal conversion happens wherever there is lesser energy difference. So, all these things can be depicted in a Jabalonski diagram, using a Jabalonski diagram. So, different molecules exhibit different phenomenon. Not all molecules will show phosphorescence and fluorescence and intersystem crossing, no. There are molecules which show only fluorescence, there are molecules which show only phosphorescence. Okay? So, using this Jabalonski diagram, we can explain that. All the molecules which absorb light will not undergo phosphorescence, will not undergo or will not show fluorescence. It depends upon the amount of energy it has been absorbed, and the amount of energy depends upon the intensity of light and also the sensitivity of the molecule. That is why in the earlier class I said that photochemical reactions are selectively activated. That is, not all molecule get activated, and in the same molecule not every part of the molecule gets activated, only certain parts gets activated, and depending upon that functional group or that molecule, the different phenomenon in the Jabalonski diagram is shown. So, using this Jabalonski diagram, we can explain the various phenomenon when a molecule is irradiated with light and when it absorbs light. How is this emission of radiation happening, or why there is no emission of radiation happening? Is it because of internal conversion or vibrational relaxation, or is it because there is phosphorescence happening and fluorescence happening? And remember, not all molecules will show the phenomenon of phosphorescence and fluorescence. Certain molecules which absorb energy, light energy, will show phosphorescence. Certain other molecules which absorb light energy will show fluorescence. That depends upon the nature of the molecule, that depends upon the nature of the functional group in the molecule. So, that is why in the earlier video I said photochemical reactions are selectively activated. Not all molecules get activated, and within the molecule not every group in the molecule gets activated. Only those molecules or only those functional group which are sensitive to light gets activated. And when they get activated, various electronic transition happens, and accordingly they will show fluorescence or phosphorescence. Now, we will be discussing in detail about fluorescence, phosphorescence, radiative relaxation and non-radiative relaxations in the next video. Thank you.